All right, so this question reads, a diffraction grating is used to measure the wavelength of monochromatic light. The spacing of the slits in the grating is 1.15 by 10 to the negative 6 meters. So I think we just saw an example where the separation was 2 by 10 to the negative 6 meters. So you get a feel for sort of a reasonable value for the distance between the lines on a diffraction grating. Although we saw, I think in the last example was 500 lines per millimeter. You could have ones that are much closer together even, you know, with 5,000 lines per millimeter was, I think, an example that we mentioned on the chalkboard earlier. The angle between the first order diffraction maxima, so that's plural, is 60 degrees, as shown in the diagram. So it's kind of like saying the zero order would be right here, but we're looking at the first order and the first order on either side of the zero order. Okay, so they're telling us that angle is 60 degrees. So really what we can kind of deduce then is that the angle is 30 degrees, theta, that we would use in the equation d sine theta equals n lambda. All right, so it's a diffraction grating question, so that's the equation that should come to mind. All right, so without that equation in mind, you're sort of just stuck. There's really no way forward, right? You have to be mindful of the equation that sort of governs the physics here. Let me go for a stroll here and ponder this. I was going to open the door, but thank Michael for doing that for me. I still want my stroll though. We have to get a little stuff. So consider this now 60 degrees in between the first order, monochromatic light. If you look at some of those answer choices, it's like 960 nanometers, 288 nanometers. Well, that's it could be light, but it's not visible. So if we're seeing this light, if we're doing an experiment in the lab, then we need to be able to sort of detect those frequencies, those wavelengths throughout it, right? So long wavelength like infrared or short wavelength like ultraviolet, right? We can't see it. All right, we're back. D is given. Theta is kind of given, right? You got to cut that in half to realize that we always measure the angle from zero order to these sort of order numbers. They're using this for 1, n equals 1. And we want to know the wavelength of the light. So let's just change it to lambda equals d sine theta over n. D is 1.15 by 10 to the negative 6 meters. Sine of 30 degrees over 1 should solve it. So we get the wavelength equal to 5.75 by 10 to the negative 7 meters. That's the same thing as 575 by 10 to the negative 9 meters. That's the same thing as 575 nanometers. So it's good to be able to go from nano to, meters, but also be able to sort of go back the other way too, right? So once you got this answer, it'd probably be pretty clear that C is the correct answer. Note that it's right there in the visible part of the spectrum, so we'd actually be able to see that if we did it in the laboratory, right? Another diffraction grating question. Let's keep a good thing going while we've got the recording going, and let's just tackle this guy right here. It's conceptual. So you look at this and you say, okay, well, not every diffraction grating question will require a calculation. We just need to know the concepts well enough that we'd be able to field a question like this quickly. White light consists of many wavelengths. The wavelength of red light R is approximately twice the wavelength of violet light V. When white light is incident normally on a diffraction grating, several spectra can be formed. Which diagram shows the possible distributions of light in the first order and the second order spectra? We don't need to do a calculation, but the equations in physics are helpful, right? They're not like, oh no, there's so many equations we've got to memorize in physics. That's what makes it hard. No, the equations make the physics easy. Try to do physics without equations, okay? It'd be like impossible. The equations tell you how these things are related. Somebody already figured it out, so we just have to say, oh, thanks. That's how the angle theta is related to n, to lambda, to d. We're sort of given that. It's good to kind of see where it comes from to derive certain equations, and we've seen that, throughout the year. But let's just really examine what is this telling us. It's saying that if we've got something with longer wavelength, okay, like red, they tell us in here, red is twice the wavelength of V. So if red is a longer wavelength light, then we put it through a diffraction grating with a given, spacing between it for a given order. So let's say we're considering the first order right now. So we plug in 1 for this. We've got red light compared to violet light. What's going to happen? Well, D isn't changing, right? That's constant for each of these examples. So we're saying, well, as I change the wavelength, long wavelength red light compared to shorter wavelength violet light, how does the angle theta that it's diffracted to change? If N is the same for each one, we're considering the first order, and D is the same, it's the same diffraction grating that we're using, then as the wavelength is longer, the angle of diffraction is greater, right? Longer wavelength, greater angle of diffraction. So we could immediately eliminate this choice and this choice because they've got the violet light being diffracted to a greater angle, and that can't be, right? The red light has to be diffracted. If here's the 0 order right here directly across from the diffraction grating, then we would expect the violet light to be diffracted to the least, and then the red light to be diffracted sort of to the most bit. Now this one you might say, well, as soon as we've eliminated these two choices, this doesn't look right. I mean, it's kind of got like the violet right there on the 0 order. And the other problem with choice D is that we've got the same amount of diffraction occurring in the second order. But again, if you sort of anchor your thoughts to this equation here, then we would say when the order number is 2, right, we're changing that. Well, now we're going to get more diffraction, right? And so there's a bigger spread sort of those wavelengths in the second order because this number is higher. And again, if we're saying, okay, well now N is 2 for a given wavelength, what's going to be the angles theta? You can see how this one sort of spreads the rainbow out twice the amount, twice the angle theta from this one here. So that's why C is the correct answer. You kind of just use that equation to help govern your thoughts. But you don't need to do a calculation.